accumulation type problem. This is a calculator problem. What's given is R of t, which is a rate at which water flows into a pipe. What's also given is d of t, which is a rate at which water flows out of a pipe. The thing to remember about this is that the rate at which the total amount of water changes is the rate in, R of t, minus the rate out, d of t. And then there's also 30 cubic feet of water in the pipe at time t equals 0. So the initial amount is 30 cubic feet of water. So then part A, how many cubic feet of water flow into the pipe during the 8-hour time interval from 0 to 8. So we're going to take R of t, that rate of change, and we're going to make it the amount of change of water into the pipe by integrating. So then part A, the integral from 0 to 8 for R of t dt. There's our setup. What I used was the function name instead of using the specific function, so that I avoid copying the problem down wrong. We're going to use our calculator for this. So here is, let me turn on. There's the function. No, that's not the function. Typing the function in. And then we're going to integrate that function, math 9, from 0 to 8. The function that's stored in y1, integrated with respect to x, gives us this amount, 76.57, rounded to 3 places past the decimal. And then moving on to part B. Is the amount of water in the pipe increasing or decreasing at time t equals 3? Give a reason for your answer. So in order for the amount of water to be increasing, the rate in has to be greater than the rate out. So we can find R of 3, and we can find D of 3, and then we can determine whether the rate in is greater than the rate out. I'm going to go back to y equals. I'm going to plug d of t into y1. d of t is negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. And I'm going to evaluate the function that I have stored in y1, which is the rate in, and the function that I have stored in y2, which is the rate out. Evaluating both those functions at t, and what I see is that the rate out is greater than the rate in. So 5.086 and 5.4. So R of 3 is less than D of 3. Therefore, the amount of water in the pipe is decreasing. Water's flowing out faster than water's flowing in. Part C says is at what time t equals 0 is the amount of water in the pipe a minimum. So we're going to, and this is a closed interval, we're going to do the candidates test. The amount of water in the pipe. Here's our endpoints. We're going to need our critical points. A prime of t, the rate at which the total amount of water is changing, is the rate in minus the rate out. And to find the critical points, we're going to set that equal to 0. So essentially what we're trying to find out is when R of t is equal to D of t. So we're going to solve that using our calculator. In y1 I have r of t, and y2 I have d of t, and y3 I'm going to put r of t minus d of t. And then I'm going to turn these two functions off so I don't see them. Before I hit enter, or before I hit graph, I'm going to check my window. I want 0 to 8, that's my time interval. I want to see where r of t minus d of t is going to be 0. So then negative 1 to 1 for my y min and y max. Hit graph. So here's the one value that I'm looking for. Second, calculate the 0. The 0 is between 3 and 4. 1, 0 between 3 and 4, so the guess doesn't matter. 3.272 is the value that I'm looking for. And then I can find the amount at t equals 0, t equals 3.272, and t equals 8. The amount at 0 is 30. The amount at any time is given by the initial amount plus the integral from 0 to whatever time r of x minus d of x, which is just r of t minus d of t. Integrated with respect to x. When I integrate the rate of change of the total amount, it'll give me the change in the total amount, plus the initial amount gives me the amount at any time t. And I can use my calculator for this. 30 plus math 9, the integral from 0 to 8, not 8, 0 to x. The value that's stored in x right now is at 3.272. Alpha y3, which is where I have y1 minus y2. Integrated with respect to x. And there's 27.965. And then we're going to do the same thing, but with 8 as the upper limit. Oops. There's 48.544. Then we got to make sure that we answer the question. The absolute min amount of water is at t equals 3.272. I think this is hours. There's an alternative justification here. What I have is that the rate at which the total amount is changing is a relative min. Looking at the graph, the rate at which the total amount is changing is going from negative to positive. So because that a prime of t, or that r of t minus dt, is changing from negative to positive, then 3.272 is a relative min, and it's the only critical point. Therefore, it's the absolute min. So an alternative justification to what we did here. And then for part D says that the pipe can hold 50 cubic feet of water before overflowing. For t greater than 8, water continues to flow into and out of the pipe at the given rates. Right, we do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. So, part D, we have our initial 30 plus the integral from 0 to w of r of t minus dt integrated with respect to t equal to 50. So we want to know when the amount of water in the pipe is going to be 50. For this problem, this is 1 point. We're writing the integral of r of t dt. 1 point for the final answer. 1 point for looking at r of 3 and d of 3. And then 1 point for the answer with justification. Part C, 1 point for r of t minus d of t as the rate of change of the total amount. And then 1 point for the answer with justification. For candidate's test problem, the justification is the table. And then for part D, 1 point for this integral, and then 1 point for a correct equation. And that is the 10 total points.